Okay, this is YouTube homework 6. So in our first question, we're looking at two gliders which are on a frictionless level air track. Initially, glider A moves to the right and glider B is at rest after the collision. Glider A has reverse direction and moves to the left. And there's a system, of course, consisting of these two gliders. So in part A, we label the direction of momentum, and so A is going to turn around with its velocity. The direction of momentum is going to be the same as velocity, and glider B is going to go from 0 to forward. And for the entire system, there is no change because we are looking at an entire system with no external forces having any effect on it. Is the magnitude of the change in momentum vector for glider A greater than, less than, or equal to the magnitude of the change in momentum vector for glider B? About that, I had to check my answer. It felt wrong for a moment there. Anyway, so the magnitudes are equal. The impulse exerted is the same on either block. Therefore, the change in momentum is opposite but equal. All right, draw an arrow for each glider to represent the direction of the change in velocity from before to after. We know that glider A is going to go to the left, as we were told that in the description, and glider B is going to go to the right. Glider B has to go to the right because, first of all, its momentum is transferred and there's no friction, or momentum's exchanged and there's no friction. Is the magnitude of the change in velocity vector for glider A greater than? Yes, it is greater than, because, and that is because glider A is 1/4 the mass. So given that the change in momentum is equal and momentum is proportional to mass times velocity, that which with a lower mass will have a higher velocity. Consider the following incorrect statement. Glider B will move to the right after this collision, but it will move faster if glider A were to come to a stop. I said that's not true, and I don't think that's possible in this scenario because there is no friction. So if that were to happen, there wouldn't be an impulse. I don't even think that's possible in this situation. But yeah, that's but with that, when there's a higher impulse, the momentum, yeah, larger impulse results in a larger a higher momentum on either block. So a higher change in momentum in either block. So that is incorrect. Ooh, let's see. Page 2. A firecracker is at rest on a frictionless horizontal table. The firecracker explodes into two pieces of unequal mass that move in opposite direction. Is the net force on the left piece always 0? There's supposed to be a not in there, so it says right now it says no, the block would remain at rest. However, it says no, the block, it should read no, the block would not remain at rest. And if the block is not remaining at rest, then there is a net force, and there will always be a net force. Part 2, is the net force on the system consisting of both pieces always 0? And that is yes. By Newton's third law, the forces should be equal and opposite of one another. Therefore, the net force on the system is 0. Is the momentum on the left? Is the momentum on the left piece conserved? No. Reason being, as Knight states in the book, you need to find the correct system to look at, and just looking at the left piece does not consist of the entire system. We need to look at both blocks, and which segues into part 4. Is the momentum conserved on both of the pieces? And it is conserved. So the impulse is equal on either block. Therefore, the momentum or the change in momentum is equal and opposite to one another. Therefore, momentum is conserved. B, a block slides down a frictionless incline. The incline is fixed in place on a table. Is net force on the block always zero? No. No, it is not. We know from the work on force that we've done that this block will accelerate with gravity, depending on this angle here. So there's a net force on this block. The net force on the incline is always zero, however. And it's kind of weird because we know that it's fixed in place, so that kind of messes with it. And because it's fixed in place, it affects the later questions down here. But yeah, since it's fixed, it can't move. So there's no net force on the block. Is the net force on the block incline system always zero? No. No, there's a net force on the block. And there isn't a net force on the incline. So there needs to be an equal and opposite force to this block that would create a net force of zero. So you'd have to change the system. You'd have to like look at the Earth, I believe. I think that's what you'd have to do, but I know this does not have a net force of zero. Is the momentum of the block conserved? No. Similar to the last answer, is just we know there is a change in momentum, and there's no equal and opposite momentum. So momentum's really just increasing as time passes by. Is the momentum of the incline conserved? Yes, simply because there is no velocity, so it remains at zero the entire time. And for the system, no, the momentum is not conserved, once again, just because there's no equal and opposite force to this block. There's a change in momentum, and it's not equal to the, so initial momentum does not equal final momentum. So momentum is not conserved. All right, so part C, the block or the incline is now frictionless. And similar to last time, no, the block is accelerating, therefore its net force is not zero. And in this scenario, the net force on the incline is not zero because it is receiving a normal force from the block. This is a little exaggerated here, of course, but it's causing a movement in the x direction. Is the net force on the block incline system always zero? And this I said yes, because the forces should be equal and opposite, just by Newton's third law. And the momentum of the block, is the momentum of the block conserved? No. Just we need to look at a different system. Momentum of the incline is not conserved for the same reason. There's a net force on it, therefore it is moving. And is the momentum of the incline of the block incline system conserved? And this was kind of tricky. I'm not sure if I'm right, but the block is moving in two directions, both the x and y axis. So it's got two momentum vectors, and the incline only has an x direction momentum vector. So I think you need to change the system. I think we need to look at the Earth as well, or possibly the table, or just another surface to guarantee that there would be no overall change in momentum. Let's see. Two blocks A and B are connected by a massless and inextensible string. Their masses are 200 grams and 400 grams. The blocks are released from rest. The pulley has negligible mass. Let S represent the system of blocks A, B, the string, and the pulley. Is the net force on block A? No. It is not zero because there's going to be a tension force causing acceleration upwards. Is the net force on system S always zero? 1 second. All right, sorry about that. I have to check my answer again. This homework is a bit trickier than some of the older ones. All right, so for the Poli part 3 or part 2, I wrote yes here, and I'll change it before I send it in, but the answer is no. There is an external force acting on this system, and we know that because there is going to be some acceleration on both block A and B. Those accelerations are equal, but we would have to look at a bigger system once again if we wanted to find a net force of zero. Is the momentum of block A conserved? No, it has an external net force, and as a result, the momentum is changing. And similarly, part 4, because there are external net forces, the initial momentum is not equal to the final momentum. It's just constantly increasing in this scenario. But if we were to change our system, it would possibly change. All right, part 3. Glider A of mass m moves to the right with constant speed. Glider B has twice the mass. In the spaces provided, draw momentum vectors for glider A, glider B, and system S. So this is an isolated system, so we know that the delta P, or that momentum is conserved. We know that glider A is going to bounce the opposite direction, and glider B is going to move in the positive direction, the same direction that glider A is moving. And this, God, I really couldn't tell exactly how to do this with only one equation, but I know that initial velocity, or excuse me, initial momentum is going to equal final momentum of block A plus final momentum of block B. The masses cancel out, and we will end up with initial velocity of block A equals initial velocity, or excuse me, final velocity of block A plus 2 times the final velocity of block B, giving us this equation right here. So I came up with these magnitudes in relation to V naught. So I have glider A will be moving negative 1/4 times V naught, and glider B will be moving in the positive direction of 1/2 times V naught. Glider X of mass 5 m, not shown in the diagram, moves to the right with speed V naught. Apply the Galilean transformation of velocities to determine the velocity vectors of A and B in the reference frame of glider X. Draw the vectors in the space at the right. Label each vector with its magnitude. All right, so I think what they're getting at here is that we know glider A is moving at the same velocity as glider X. Therefore, in glider X's reference frame, glider A is not moving. I think this is supposed to be before the collision, just based off these later questions. So, and glider B will of course have a negative V naught velocity, and that gets here into momentum. If they both have the same velocity, then which is 0, then in the reference frame there will be 0 momentum. However, glider B will have a negative momentum. I gotta get to this quick. Come on. Okay, so basically we're on the last answer here, and we're comparing momentums in the reference frame of X, and because the velocities are both the same, that is 0, then neither of them have any momentum, because momentum is mass times velocity. And the final problem, no, a change in the magnitude of velocity would not have any, or excuse me, mass would not change